Hello! Welcome back to Chem 121 for the last time. Let me mute the music on my side here. Ah! All I did was make it louder. That's not what I wanted. Okay. There we go. Alright. Hi again. Welcome back to Chem 121. This is the last time we will meet because it is the final exam review session. And the final's tomorrow, unless you have asked me to move your final, in which case it is today or Thursday or Friday. So we're going to go over the questions in the order I got them. I also have a bunch of questions that a student sent, and let me put those on the screen real quick too. Notepad, there it is. So here are those questions. Oops, I didn't quite capture all of them. There we go. So we will do those after I do the questions in the chat. So please populate the chat with any questions you might have. I will go over them in the order that I get them. If I have questions about your question, I will let you know when I get to them. So let's start here. So what volume of liquid in milliliters has a mass of 3.81 kilograms? I need the stylus. There we go. And then I need a color that is not white or black. I need... This'll work. Okay. So I have this... Yep, I'm not using the pen tool. There we go. I have this mass for my object. My liquid, that is. Did I send the announcement out to the wrong class? This is supposed to be 121. You know, I bet I sent the announcement to the wrong class. Oh, frickin' A. Yeah, I sent it to the wrong class. I apologize. Let me send a new announcement out. If you are in 140, your review is at 230. This is why I hate Canvas, is because my classes are labeled Blueprint Hillman and a bunch of numbers, and I always get the wrong class. Okay, so correction, review session starts at 2:30. Review session for 140 will begin at 2:30 today. I'm very sorry about that. So this announcement will go out at 12:42. Okay. Yeah, I fixed that. And then let me post in the 140 Discord real quick. For Chem 121, please ignore. Our review for 140 is at 2:30 today. Okay. So I apologize. If you were here for 140, yours is at 2:30. Okay, now I gotta go back to the problem I'm working on. So again, I apologize. I need the density of this liquid, which is density of the liquid. And of course, Photoshop is going to act up on me. Great. Density of the liquid is 0.895 grams per milliliter. Oh, for fuck's sake. Okay. Now, you'll notice that this unit and this unit, those don't really match up, right? So we're going to have to convert one of these units to the other. I always find it easiest to just convert the unit that isn't the compound unit. So I could take my kilograms and do this to it. And say that in a kilogram there are 10 to the 3 grams. Oops. Don't need that dot there. So this would be the number of grams for this sample. And if I wanted to find its volume, I could then multiply by the density, right? Because I could do something like this. And we know that the density of the liquid is 0.895 grams per milliliter. And so then we can just go to the calculator. 0.895. So that's the answer I get for 3 sig figs. All right. There's a question here from Mr. and Mrs. Hartman. Go over the highest boiling point between a few different elements. I'm not sure what you're asking because different elements have different boiling points, but we haven't really discussed that. Do you mean boiling point for like mixtures or not mixtures, but like different compounds or stuff with like intermolecular forces? Can you be more specific, I guess, is what I'm asking there. Is this for Chem 140? No, it's for Chem 121. Hopefully people are in the right spot. I see that the number of people that are viewing has changed drastically, so again, I apologize for that. Let's see here. Chapter 6, if 8.50 moles of pentane are reacted with abundant oxygen, how many moles of H2O are produced? Okay, so for that, we have to write out the balanced chemical equation for the combustion of pentane. All right, so now we're going to balance the equation. So each side has carbon, hydrogen, and oxygen. So I got 5, 12, and 2. And then over here, carbon, hydrogen, and oxygen. 1, 2, and 3. So we have to balance the equation first before we can do anything with it. And once we have done that, then we can do the calculation. So I have 5 carbon on the right. They all have to end up on the, or I'm sorry, 5 on the left. They all have to end up on the right here. So I have to have a 5 there. And then I have 10 plus 1 is 11 oxygen. Because I have these 10 right here plus this one. Then for hydrogen, if I have 12 on the left and they come in pairs, that means I have to do something like this. So that would be 6 times 2 is 12 hydrogen. And then my oxygen would be 5 plus 2 is 10. Or 5 times 2 is 10. Plus 6 times 1 is 16. So that's what that looks like now. And then to balance my oxygens over here, I just do that. So that should be the balanced equation for the combustion of pentane. You take a pentane and 8 oxygens, you get 5 CO2 and 6 H2O out. Now, we're not going to burn 1 pentane. We're going to burn 8.50 moles of pentane. So we can do that calculation now. And that's going to, what do we want? Moles of H2O. So we know how many moles of H2O are produced per mole of pentane. So if I put one of these in, because there's a 1 in right here, in this blank space, and then right here, we've got a 6 for H2O. So every 1 mole of pentane I combust, I create 6 moles of water from the reaction. And so this would be 8.5 times 6, whatever that is. 8.5 times 6 gives us 51.0 moles of H2O. All right. Sophia's question's from 140, so I'm going to skip that because that's not for this class. Unless it is, then please correct me. But I believe that that's a 140 question. Because your Chapter 6 quiz doesn't have naming on it. How many moles of silicon are in a sample containing this many atoms of silicon? We could do that. So we know that in 1 mole of something, we'll just write atoms, there are Avogadro's number of those atoms. So if I have oh my goodness, I hate Photoshop when it does this. I'm convinced this is a Windows 10 problem. Because it was never this bad in Windows 7. We can do something like this. And these are silicon, so I should indicate that. So in 1 mole of silicon, there are Avogadro's number of atoms. And so we'll punch that into the calculator. 2.30 times 10 to the 24 divided by parentheses 6.022 times 10 to the 23. And I get 3.819, which I'm going to round to 3.82 moles of silicon. So for a lot of these problems, really the trick is doing the relationship. So remembering that the relationship between atoms and moles involves Avogadro's number, or that the ratio of moles of something to moles of something else, you do that in the balanced chemical equation. Things like that. That's really a lot of the math in chemistry, is just realizing what all of the possible conversions are and then doing those as they're needed. Okay. So the intermolecular forces part of equations. So let's suppose that I have 3 liquids. So I have water. Let's see here. We'll say formaldehyde and hexane. So what I'm going to do for these three liquids is I'm going to draw their Lewis structure here. So there's water. Here's formaldehyde. And then, you know what? Hexane is way too big, so let me make this smaller. Let's do butane. This is still way too big. This is my life now. I have to write H's over and over. H, 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 H. So particles is intended to be either atoms or molecules or formula units or whatever the context of the problem requires it to be. Because really what you were doing is counting something when you were counting particles. And so you are counting whatever is there. So it could be atoms, it could be molecules. Whatever is the appropriate term for the problem you are working on, that is what is intended by particles. I just didn't want to write in a box atoms or molecules or ions or formula units because then it's just a bunch of terms in the box. So particles is meant to be a colloquial catch-all, I guess we'll say. All right, here are my molecules. So what we're going to do is we're going to list off all of the intermolecular forces that they have. So water has dispersion because everything has dispersion. It's also polar. But because it is an oxygen, nitrogen, or fluorine, and a hydrogen is bonded to an oxygen, nitrogen, or fluorine, it's capable of hydrogen bonding. And so this is the most important one. This is the strongest. Formaldehyde has dispersion because everything has dispersion. And it has dipole forces because it has a dipole. It looks like this. Because oxygen is more electronegative than the hydrogen end. But it cannot hydrogen bond because there's no hydrogen attached to this oxygen here, right? So all it can do is dipole. That's the best that it's got. And then butane is just dispersion. That's all it can do. It's just sitting there. And so what we would conclude is we would say stronger intermolecular forces hold molecules more tightly together. I ran out of space to write that. And so as a consequence, when you have molecules that are held together, the boiling point increases the stronger they are held together. The reason for that is because molecules are trying to escape from each other into the vapor phase. If they are all held together tightly, they're less able to do that. They are being held back. So molecules that stick to each other more effectively cannot leave the liquid. And you have to heat them hotter and hotter and hotter and hotter in order for them to do so. So what we would do is we would expect, well, water can hydrogen bond. This is the strongest intermolecular force. So its boiling point would be the highest. For formaldehyde, dipole interactions are strong, so we would expect its boiling point to be in the middle. And then for C4H10, dispersion is weak, so we would expect its boiling point to be the lowest. Now remember that mass has something to do with this too. And as you increase mass, you increase the dispersion force. So I tried to pick molecules that were similar in mass. C4H10 might be too big, but I would expect its boiling point to be low. In fact, I can go look this up. Let's see here. So, boiling point formaldehyde. So, -2, and then boiling point butane. Yeah, I chose a molecule that's too big. So, it turns out that these two are actually relatively close to each other, and it's hard to make a prediction. But if I was going to ask you a question on the exam, it would be along these lines. Sort by the forces, and then I would do all of the details later. This is why I specifically ask you to give me questions, is because I can't make a question without doing all the research. And so now that I've done the research, I wouldn't have asked you this question, because it turns out that this one is actually swapped with that one. But you wouldn't predict that based on what we've learned, right? Dispersion is weaker than dipole, so we would put dispersion as a lower boiling point. But that's the gist of how we determine boiling points based on intermolecular forces. Pick the intermolecular force that is the strongest. That substance has the lowest the highest boiling point. Pick the intermolecular force that is the weakest. That substance has the lowest boiling point. Okay, so I'm out of space here, so we're going to do that. Oops. Okay, and then I have other questions from a student here, which we'll put on the board. Boop. Oh, I didn't catch everything. Hold on, there we go. So there is a question about quiz 3. This answered the questions about which ones are stronger, weaker. Yeah, that's what I want you to do. Is I want you to just say, okay, if you have stronger intermolecular forces, the boiling point must be higher, and so on and so forth. So on the screen here, I have the question, check the elements that would react similarly with iodine. Obviously, I don't have those elements on here because I don't have that quiz question handy. But remember that I don't have p-table open. Let's get this open. I gotta add a window capture. Window capture 2. Alright, well we can do this. Oh, apparently we can't. That did absolutely nothing. That's super obnoxious. Why isn't this showing up? Oh, is it just ginormous? Is that the issue? Wow, I've broken everything. You know, we're just going to delete that one. There we go. We'll create another one. There. We don't need all of that at the top there. We just need this part. All right, so here's our periodic table. And so if our element is iodine and we're looking for elements that react similarly to iodine, remember that everything in the same group, which in this case would be group 17, the halogens, should react similarly. So you'd want to check if these options were available. Fluorine, chlorine, bromine, astatine, and then tennessine. Don't worry, I won't put tennessine on your exam because it's radioactive, but elements in the same group react similarly. So that's something we covered in chapter 3. So you would check all of these elements here. You wouldn't check iodine because that's the question we're asking. Okay, so I can do this. Can I scroll this? No, I don't have a scroll bar. All right. So consider the balanced equation shown below. If 40.2 grams of whatever that is, C2H3N, I don't know, are reacted with excess O2, how many grams of CO are produced? Give your answer to the appropriate number of sig figs. So let's write down the balanced chemical equation. And then what I got? 8CO plus 6H2O plus 4NO2. And then I have 40.2 grams of C2H3N. So I want to get to grams of CO, according to this problem. So that means I got to do grams of this, which I'm going to then turn into moles. When in doubt, turn into moles, right? And then my question is asking about CO, so I can turn moles of C2H3N into moles of whatever I want. Why not moles of CO, which you could turn into grams of CO? So we can do that. So grams of C2H3 and moles of C2H3N. In 1 mole, how many grams are there? Well, we need to go look that up on Lentech. So let me get Lentech out. C2H3N weighs 41.05 grams per mole. We could use the periodic table to do that. Just add up all the C's and H's in the N. Now we'll turn this into carbon monoxide. How many C2H3Ns? We put in 4. That's this number right here. How many COs do we get out? We get out 8. And then we can turn that into grams. We need its molar mass. Carbon monoxide weighs 28.01 grams per mole. And there you go. Let's punch in all the numbers. 40.2, 8, 28.01, divided by parentheses, 41.05 times 4. And you get 54.86, which will round to 3 sig figs. There you go. All right. Unfortunately, when I was sent these questions, I didn't get all of the choices that are in there. So this question in its context doesn't really make sense, but what we can do is just make a few sample choices here, so. Oops, hold on. All right. So there's our that's our equilibrium expression that we have. And so what our equilibrium expression is telling us is that if I mix these things together, I will have some mixture at equilibrium. And what I want to know is figure out which changes would make more CH4. Oops. How would I increase the amount of CH4? Well, if I add in any amount of product, so let's do these one at a time. So if I were to add extra product, so I dump CS2 into the reaction mixture, I'm no longer at equilibrium. I have too many products, right? So I would need to get rid of the excess products that I have, move in this direction, and I would increase the amounts of these. So to add more CH4 to the mixture, to the equilibrium mixture, I should say, we would add products, such as CS2 or H2. Now I gotta get rid of all these arrows again, so that's kind of obnoxious. But I do have a solution for this. And that is to push this set of keys. Boop, there we go. Now I don't have to worry about that. Okay, what else could we do? So I could add products. I could also remove reactants, such as H2S. So if I reduce this amount of stuff, now I have too few reactants, right? So in order to make more reactants, I would have to remove products. So if I remove H2S, I could facilitate the production of CH4 by consuming the products of the mixture and turning them into reactants. Now, obviously, if you remove CH4, you aren't increasing it, so we're not going to do that. But okay, so now I can just do this, and it will stay there. What else could I do to the reaction mixture? Well, what about heat? If I want to play with the temperature, adding heat or removing heat would either increase or decrease the amount of CH4. So if I add heat, then I have to get rid of it, and I have to get rid of other things to go with it. So adding heat would not cause more CH4, but you know it would is doing the opposite of that. So if I wanted to remove the heat, so by putting this in a cold bath, then the reaction has to fill in the heat that was lost, and in doing that, it will make more reactants and reduce the amount of products. So we could reduce its temperature here. Put it in a cold bath. There's one more thing that you can do, and that is to play with pressure, because we're saying that all of these are gases. Even though I know CS2 isn't a gas, but that's okay. Which side has more or fewer moles? So if I count the number of moles here, I get 1 plus 2. I don't know why this isn't painting. Probably because I don't have it select all. Let's see here. Yeah, there we go. And over here I have 5 moles. If I want to push things toward this side, then I need to increase the pressure, because if I make the container real small and the pressure goes up, remember equilibrium is going to try and get back to the original pressure, right? So it'll do that by moving in the direction of fewer moles. So these are all ways that we could increase CH4 in the mixture. Now, if you wanted less CH4, you would do the opposite of all of these things. So instead of adding products, you would remove products. Instead of removing reactants, you would add reactants. Instead of reducing the temperature, you would heat it up. And instead of increasing the pressure, you would decrease it by making the volume really big. So that's an example of Le Chatelier's principle. Oops, that's not what I meant to do. All right. This is from the worksheet. So first balance the, first neutralize the acid and base, then balance the equation. So we could do that. So here's A. We've got blank. Well, I mean, I could do that if my Photoshop wasn't so laggy. All right, so remember what we do with acid-base reactions. First, we have to dissociate all the parts. We just write them all out. And then we got to find water. So here's a water. Boop, boop. Oh my goodness, I hate you, Photoshop, today. There. But I've not completely neutralized the acid, because I still have some base here, right? So I need to add extra acid. So now I can go boop, boop. And I have neutralized all of the acid in the base. And then everything else that's left over must be the salt. So that would be calcium acetate. I had to cram that in there. There's a 2 outside of that parentheses. All right, that was the first one. For the second one, same deal. We'll split up all of our pieces. So here's our acid. And then here's our base. So I've got 1 water so far. But I did not neutralize all of the acid. There's still some that's left. So I need to do this again. Then I'll neutralize the remaining acid and base. And everything that's left over is the salt. And there you go. So that's B. Last we have phosphoric acid here. And barium hydroxide. And I'm going to need a little more space for that. There we go. So same thing as before. We'll just split this into all of its pieces. So there's my phosphoric acid. And then my barium hydroxide here. We can do that. So I've got 1, 2, 1, 2. So here's some water I can get rid of. Not get rid of, create actually. But I did not neutralize all of the acid, so I need to add more base. So I'll add another unit of barium hydroxide. And then we can neutralize this one and that one. But now I haven't neutralized all the base, so I need to put another phosphoric acid in. Remember, these come in as they are. So if I add barium hydroxide, I had to add 2 hydroxides with a barium. Can't just add 1 of whatever I need. Got to add them in the chunks that I have. So now I have excess acid, so I got to add more barium hydroxide. And that actually turns out to be enough. So there's a water, there's a water. Everything else is the salt. So now I'm going to count up how many of these I had. So I put in 2 of those and 3 of those. I made 6 water. And then my salt was barium phosphate. There you go. All right. Those are all the questions that I had, but we're due for a break now anyway, so let me close that off the screen. So what I'm going to do is I'm going to put the break timer up here. I don't have a clock. Hold on. There we go. This is going to yell at me real quick. Come on, I know you're going to ask me to update you. There we go. All right. I'm going to start the timer. We'll put the Wii Shop music back up because it's so catchy. Go ahead and post more questions into the chat that you might have, and if there aren't any when I come back in 10 minutes, we'll adjourn from there. So I'll see you in a bit. Alright, I'm back. So, it doesn't look like there are any other questions. Sorry, I'm just looking up something really quickly. There you go. So, I didn't receive any other questions in the chat, so I guess that's all we are really going to do today. Excuse me, I had to stretch. Ugh. So, let's see here. Final exam is tomorrow, unless you have sent me an email saying, like, hey, I want you to change my final exam time. Make sure that you get that into me by tonight if you want me to move your exam. Otherwise, you're going to have to take your exam on Wednesday or whatever day you've asked for. Lab worksheet number 5 is due tonight. It closes tomorrow. And then finally, anything NQA that you might have, make sure that you get that done by Friday, because that's when I'm going to compile all the stuff for grades and get all the grading done over the weekend. I just want to thank everybody for coming to the review session and for being a part of the class. There are no more lectures. There's nothing really else for me to do or say. It's all up to you now. So I just want to wish you very well. Thanks for everything. Thanks for being a part of all of this. And I will leave it at that. Best of luck on the final.